Okay, so in this journal, what you're going to be doing is using those fundamental trig identities that we learned last time, try writing tangent in other ways. So when I'm trying to rewrite tangent, right, there are many ways I can go about this. So tangent, let's think about it. There's the Pythagorean theorem that says that 1 plus tangent squared equals secant squared. So notice that here I just want to get tangent value, tangent squared specifically. So if I want to get this tangent squared by itself, I need to remove this 1, right? So if I remove this 1, I'd basically be subtracting both sides by 1. So that would obviously cancel, bringing down the tangent squared. And so then this side is secant squared minus 1. So it looks like tangent is equal to secant squared plus 1. So I can say that tangent squared is equal to secant squared minus 1 is one way, okay? So I'll put like this one would be my first response. Another way you could do this is think about what tangent is using the quotient rule. So tangent is equal to sine over cosine based off of the quotient identity. And so if you want tangent squared, right, basically you're squaring this entire thing. And so we've learned that if you square something that's a fraction, you square the top and the bottom. So in other words, if you were to square this, this would be sine squared for the top and cosine squared for the bottom. So you can even say that sine squared plus over cosine squared is also equal to tangent squared. So you can replace tangent this way, or you can replace tangent this way. Either one means tangent squared. And that's all I can think of as far as identities go. So hopefully that gets us warmed up today, because I want us to get used to making sure if we want to change a trig expression that you can rearrange things in a identity or even square things if needed. All right, so here what we're going to be doing, kind of like what we did last time by simplifying trig expressions using identities. In these problems, you're actually given a left-hand side and a right-hand side. So what you're going to do is prove that the left-hand side is equal to the right-hand side. So you're going to try to prove that this equation is equivalent. So what I like to do is just start with my left-hand side. I'm going to call my left-hand side LH, and I'm going to basically simplify it until I get it to equal the right-hand side, or RHS. So I want to show this type of equivalence. And to do that, we have to use those trig identities. So I need to prove that this side is equal to this side. So starting on the left-hand side, you're always going to start on the left-hand side. Let's try to change this here to make this look like cosine. Let's think about it. Well, this doesn't have any cosines right now. Maybe I need to use the identities and change what cotangent and cosecant means. So cotangent, we learned last time, is actually cosine theta over sine theta. So instead of writing cotangent, I can write it as cosine over sine. And then for cosecant here, if I use the reciprocal, that's 1 over sine theta. So I've changed this guy to look like cosine over sine. I've changed cosecant to 1 over sine. So from here, what I can do is divide this fraction with this fraction. And to do that, I need to flip this bottom one. So I'm going to flip the 1 over sine. So the top stays the same, cosine theta over sine theta. And so if I flip this here, that's going to be sine over 1. And so if I multiply this, sine and sine cancel because they're diagonal of each other. And if I multiply this straight across, I have cosine over 1, which is just cosine theta. And so I've basically matched up this side to look like that right-hand side. And so I'm done verifying. So the nice part about these problems is, unlike the problems we've done before where you just kept manipulating until you couldn't manipulate anymore. These problems, you actually have like a stopping point until basically you know you're done when you get the left-hand side to look like the right-hand side. So let's try that with this one here. This one can be a little bit tricky, but start off with the top here, because what I immediately notice is that tangent squared plus 1, this comes from the Pythagorean identity. So there's a Pythagorean identity that says if you have tangent squared plus 1, that's going to equal secant squared theta. And so to look at this here, that tangent squared plus 1 is basically directly equal to secant squared. So I can replace the numerator with secant squared theta. The bottom is just a secant theta, and if you notice the right-hand side here, you just have a secant to the first power. Well, because there's a secant squared on the top and a secant at the bottom, you can cancel out a secant in the bottom, which you need to cancel out one in the top. And so if you cancel one in the top, you're just left with secant. The bottom's been fully canceled. So now you're just left with one secant. So secant to the first power, and so that looks like the right-hand side. So I'm done verifying here. Okay, so again, we're using those trig identities to help manipulate this until we can get the left-hand side to look like the right-hand side. So here are a few more that we can try out. So this one is 39 in the homework. So here, what I notice immediately, again, I have that tangent square plus 1. And so previously I was saying that tangent squared plus 1 is equal to secant squared theta. And so I can replace all of this with just secant squared theta. I'm going to bring down the cosine. And these two are multiplying each other since that was like a parenthesis. So we are multiplying these two. And the other side here is 1, right? So I got to make this look like a 1. So first off, what I notice is I got a secant. So secant has a reciprocal identity of 1 over cosine, right? Secant is 1 over cosine. But because this is a secant squared, this needs to be a cosine squared in the bottom. And then the other side here is just a cosine squared. And notice if I multiply this and force this to be a fraction by putting it over 1, and I multiply this, the diagonals are both cosine squares, so they cancel. So you really, if you multiply this straight across, you just have a 1 in the top and a 1 in the bottom. So you have 1 over 1, and 1 over 1 is just 1. And now this looks like the right-hand side, so I'm done verifying. Okay, so let's try out the bottom here. So immediately in the bottom, what I notice is You'll notice anytime I notice a square, like a trig that's being squared, I'm jumping to the Pythagorean identity, all those three, right? And what I notice is that I have a sine square and a cosine square. So I'm going to buddy these two up. I'm going to put them next to each other. Because I notice when sine and cosine are together, right, when they're together and they're both squared, they actually form something on let me write that in pink so that way we can see that they're different. So when you take cosine squared and add it with sine squared, they actually add to give you 1. They can be replaced. So these two, basically when you add cosine and sine squared together, you get 1. And so now I have 1 plus tangent squared theta. Well, 1 plus tangent squared is just, again, secant squared. So this can be replaced as secant squared theta. And notice how the right-hand side here is secant squared theta, and I got to that value. And then I'm done. I verified that the left-hand side looks like the right-hand side. All right, so here I have some problems where I have a secant. Oops, that's not my mouse. I have a secant to the 4th power here, and then I have some tangents on this side. So I need to make secant somehow look like tangent. So I need to be strategic about this. So before I go into this problem, let me give you a problem where you have x's. So I wonder if I can bring this down just a little bit. So you remember back in like algebra 2, you had to do like factoring out numbers. So if you have x to the 4th power, and let's say this is x squared, kind of like these two, right? Instead of secant to the 4th, I have x to the 4th, and instead of secant squared, I have x squared. And your teacher might have asked you, like, try to factor out as many x's as possible. So what I notice here is like the lowest power here is x squared, so I'm going to factor out an x squared. But I leave something behind when I do that. With this one here, if I took away 2 of the x's, I took it out a square, that means I'm left with x to the 2nd power. If I took away 2 x's here, I'm actually just left with a -1. Notice if I were to redistribute, I get back to the same expression. So x squared times x squared gives me x to the 4th. X squared times -1 gives me negative x squared. And so I have simplified this a little bit. And so what I'm saying here is basically we're going to try to pull out the least amount of secants. So the least amount of secant is secant squared. So if I were to pull out a secant squared, I leave behind something. For this term, if I pull out 2 secants, or secant squared, I'm left with behind a secant squared theta, 2 secants. And then if I pull out a secant squared here, I'm basically left with just 1, right? A -1. So notice if I were to redistribute, secant squared times secant squared gives me secant to the 4th. Secant squared times -1 gives me negative secant squared. So what I notice immediately is that we have some secant squares. And so there are some identities that can help us out, like tangent squared plus 1 equals secant squared. So notice here I have like a secant squared. And so I can change that to making this a secant -1 if I subtract the 1 over. So tangent squared comes down, and you have secant squared -1. So that means I can replace anything that looks like a secant squared -1, like this, into tangent squared. So I'm going to change this guy to tangent squared. And then this here, what I notice is like my answer is written as tangents. So I really need to change the secant into a tangent, and I can do that by using the identity from the very beginning. So secant squared is equal to tangent squared plus 1. So I'm going to replace this here. So instead of writing secant squared, I'm going to replace it with tangent plus 1. And I wrapped it around parentheses because I'm trying to multiply this secant with this number here. So I might put in parentheses just to be safe. So from here, I need to distribute the tangent. So tangent times tangent squared. So tangent squared times tangent squared gives me tangent to the 4th. Tangent squared plus 1 gives me tangent squared theta. And I think this looks like this side here, and it does. And so I'm done verifying here. So if you notice that you have some high powers, try to maybe factor out some power so that way you have something to work with. You might never know, you might be able to replace more after you factor it out. All right, that's it for this video.